Okay, so let's go ahead and video some more of the notes that we have here. The next topic that we're going to talk about is gravitational potential energy. So the last part of our notes we finished was the flow chart over here regarding energy. Now let's talk about each particular type here, and we're going to talk about the equations and how to work them out. Then we're going to combine them and talk about work energy theorem. So gravitational potential energy, or known as GPE, is when the units are going to be in joules. Okay, any kind of math equation, not just in physics, but also in chemistry. If it has to do with energy, then it's a joules for the SI unit. Next question says here, well, what is potential energy? Now, potential energy is stored energy as the result of its position. Okay, result of its position. Examples. It says here the heavy ball of a demolition machine is stored energy when it's held at an elevated or elevation position. A drawn bow and arrow is able to store energy as a result of its position, okay, due to its position, and that's the key part there. So we've got a little picture down here below, and we got a few questions. Letter A. Letter A says, using this picture over here, where will the ball have the highest potential energy and why? Well, for this picture here, at the top highest position is when it's going to have the greatest potential energy. Okay? Why is that? Because of its position. All right? Because of its position being higher up. Where will the ball have the lowest gravitational or the lowest potential energy and why? And that's going to be at the bottom. And it's going to be at the bottom because, again, of its position. Okay? Due to its position. That is the key word when it comes to potential energy. And I say potential. I didn't say gravitational potential because we have two types of potential energy. We have stored gravitational potential energy, and then we have stored what we call elastic potential energy. And we'll talk about that on the next page. So it says here how to solve for potential energy. So this equation that we're talking about first is going to be potential energy, but it's going to be gravitational GPE is a shortcut, GPE. Now, when we write it out, you can see it written out as GPE, or you may see it as PE lowercase g, gravitational potential energy, equals mass times gravity times height. Okay, so gravitational potential energy is what GPE is, and the SI unit is a joule because it has to deal with energy. The M stands for mass, and it needs to be in kilograms. The gravity for G, we talked about gravity last semester. We know that it's 9.81. I know it's a negative value, but we're going to ignore the negative because that is a direction. Meters per second square is the SI unit for gravity. Height is in meters, okay? Don't forget your SI units. That's what they need to be in before you do the equations. Let's look at this first question down here. A cart is loaded with a brick and pulled at a constant speed along an inclined plane to the highest or to the height of a seat top. If the mass of the loaded cart is 3 kilometers, so that's the mass, and I meant to say kilograms, I apologize. And the height of this seat at the top is 0.45 meters, h. Then what is the potential energy of this? question mark GPE. And again, our equation for GPE is mgh. I have mass, which is 3 kilograms. I have gravity, which is 9.81. We ignore the negative. And then the height is 0.45 meters. It must be in meters. Do your multiplication. When you multiply those numbers together, you should get an answer of 13.24 joules. That's your SI number. I'm sorry, that's your answer, and that's the correct SI unit. Now, I'm going to pause real quick because GPE can be put into the triangle. If you don't like the triangle, then close your ears right now. If you do like the triangle, well, then pay attention. Now, all 3 parts of my equation over here are being multiplied, so I need to actually manipulate and change the triangle so that way there are 3 parts at the bottom because those 3 parts are multiplied. So M, G, and H go at the bottom of the triangle. That line separating means multiplication. And look at that, 2 multiplications, 2 lines. What's left over? Gravitational potential energy. And then you place that into it. So this is what the triangle looks like for this equation. Next question over here. It says here that if a force of 14.7 newtons is used to drag the loaded cart from the previous question along the incline for a distance of 0.9 meters, that's some type of distance, well then how much work is done onto or to the loaded cart? Well, I know that work equals force times distance because that was on a couple of previous pages. And if I'm looking for work, I actually don't need to change anything, okay? All I need to do is plug in my number. So 14.7 newtons multiplied by 0.9 meters equals blank joules. Remember, work is also in joules, okay? Work is also in joules. Alrighty, let's keep going. I'm trying to make sure that I didn't mess up on anything. You might see work as a Newton meter because that's a Newton, that's a meter, but we prefer it to be in joules, okay? Let's keep going. Now, looking at the diagram over here to the right, what's the potential energy of this rock? Question mark, GPE. Okay, well, GPE equals mgh. I have it, the variables, and they're in the correct SI units for mass. Gravity is 9.81, and the height is 100 meters, so everything is correct. I'm going to go ahead and multiply my answers together, and I'm going to get the SI unit of a joule. And there you go. You need to do the math and get your answer there and over here. The next one, elastic potential energy. This is also a potential energy. Now, GPE up here is an equation that you talked about in school, in middle school actually. And elastic potential energy is actually an equation that's not taught then. So this one's probably a brand new equation for you that you probably haven't talked about this vocab. This might be something just new for you completely. So let's look at that. We have some blanks to fill in. It says here that elastic potential energy, or the shortcut is PEE, lowercase e, is the energy stored in quote unquote elastic materials as a result of their stretching, or it can also be their compression. And we'll talk about that in the next paragraph. It says here examples of a rubber band, a bungee cord, trampoline, a spring, it's a very common one, a drawn bow and arrow when you pull it back, a scrunchie. There's a whole bunch. The elastic in your I don't know, pants. It says here that the amount of elastic potential energy, which is stored energy, such as a device related to the amount of stretch of that device. Now, the more stretch, the more stored energy it's going to have. The next one, springs are special instances or special instance of a device that can not only store elastic potential energy, but it can be due to either the stretch or the compression. Kind of like clicky pens. Oh, look, I've got one right here. So I'm sure all of us have got clicky pens. And what do you do with the clicky pens? You probably opened them up before. And when you open up the clicky pen, you've had that little bitty tiny spring in there. Now that little spring that's inside your clicky pen, when you took it out and played with it, you can compress it or pull it apart, or you can compress it together. So you can stretch it apart and you can compress it together. So springs are a little special where it can do both. It can stretch apart or together. A force is required to compress the spring, and the more compression there is, the more force that is required to compress it further. The next part, Hooke's law, says here though, if a spring is not stretched or compressed, it's just sitting there, then it is said that there is no elastic potential energy that's stored in it. And we say that it is in equilibrium position. And when it's in equilibrium position, then the PEE is actually 0 joules. So you can have an answer of 0, not just for elastic potential energy, but stored gravitational potential energy too. So a 0 answer is a valid answer. All right, let's keep going. Let's look at that equation, because elastic potential energy has an equation here. And again, I know this is a new equation for us. PEE equals 1/2 times lowercase k times d squared. That is the equation for it. Now, this can be put into the triangle as well. And when I look at this, cover up the equal part, there's 3 parts here and they're all being multiplied. So on this triangle at the bottom means multiplication. And I actually had to manipulate this and add an extra line. So that way I can say the 1/2 is over here, the k is down here. Again, it's a lowercase k. And then distance squared. What's left over? PEE. Okay, so that's what the equation looks like. It is on the formula chart. That's what the triangle looks like. PEE stands for elastic potential energy. The SI unit is a joule. A K, actually a lowercase k, stands for spring constant, which is in a Newton meters. And a spring constant is a particular number for that material being used. For an example, I've got a rubber band here, and I've got a whole nother rubber band right here. 2 different rubber bands. This one's a lighter and this one's a little darker. Yes, this one's smaller in size and that one's longer. Now, when I stretch the rubber bands apart, this one's really flexible. This one is definitely tougher, stronger. Obviously, they are not made from the same material. And since they're not made from the same material, then that means that they have 2 different K values or 2 different spring constant. So this stretchiness is what we call the spring constant. I don't care if we're talking about a trampoline, if we're talking about a spring, a bungee cord, a rubber band, a hair scrunchie, a bow and arrow, whatever it is. Every type of material out there is going to have a particular spring constant number. So for those equations, either they are going to give you the spring constant or you're looking for it. But it's not a number that you're having to memorize like gravity. Okay, there's no way you're going to know all the spring constant numbers out there. And it's not a constant like 1/2, right? So that's what the K value is. And don't forget, you might see lowercase d or you might see a lowercase x. They mean the same thing, which stands for distance. And a distance is in a meter, okay? Let's turn the page. Looking at a few examples. So it says here though, if a spring has a spring constant, so they're giving me the K value. How much energy? Question mark. Once I know that we're talking about a spring, something stretchy, or a K value, then that's PEE. Is required to compress the spring a distance of 0.25 meters from its undisturbed position. So my equation for PEE equals 1/2 times K times D squared. If there is going to be a mistake, squaring the distance is probably the number one mistake students forget to do. The other mistake that they forget to do is when you're looking for the distance, don't forget to square root it at the end. So I'm going to change 0.5 from 1/2 to 0.5 because that's the same thing. And it's a lot easier in physics to work with decimals than fractions. The K value is 400. The distance is 0.25. So multiply those three numbers together and you're going to get an answer in blank joules. The next question, number 2. Number 2 says, when a 13.2 joules of energy is given, okay, to a vertical spring. Okay, I know it's a spring, so now this joules is a PEE number that's compressed to a distance of 0.0593 meters. Find the spring constant, question mark K. So we're actually looking for the K value. So PEE equals 1/2 K D squared. Or let's go ahead and fill in the numbers now. 13.2 equals 0.5 times K, which is what I'm looking for, times the distance, 0.0593 squared. Okay, so let's go ahead and square that number, and we're going to do our math so that way we can isolate and look for the K value by itself. So 0.0593 this number becomes 0.0035. I'm going to round it to 2. And let's multiply that by 0.5. I get a number of 13.2 equals K times 0.001758. Divide by 0.001758. That cancels out. Divide this side, 0.001758. The K value or spring constant equals, well, let's look at that. 13.2 divided by 0.001758 comes out to 7,508.53. What is the SI unit for the spring constant? It is a Newton meter. Okay. Double check my math, but I think that's correct. Next one, compress the spring or a compressed spring that obeys Hooke's law, and the equation is called Hooke's law, to the potential energy. And what kind of potential energy, since we're talking about a spring? PEE. If the spring constant is 400, that's the K value. Find the distance, question mark distance. Okay, my equation for PEE equals 1/2 K D squared. I'm actually looking for the distance, so let's go ahead and write in the numbers 18. Change 1/2 to 0.5. The K value is 400 times distance squared. Let's go ahead and change that, the numbers over here. 400 times 0.5 is actually 200. So divide by 200 on this side. That cancels out. Divide by 200 on this side. The distance squared equals 18 divided by 200, 0.09. Not my answer because that is a squared value. So now I need to square root it. So let's go to second key square, 0.09 equals a distance of 0.3 meters. And that's a correct SI unit. Okay, let's keep going. The next one is kinetic energy. And you talked about kinetic energy over at middle school. So this should be fairly simple for you here. We have a couple of blanks. The amount of kinetic energy, it says here, of an object depends upon two variables. One of the variables is the mass of the object, and the other variable is the velocity of that object. Now, the equation, which is a pretty simple one because you've talked about kinetic energy in the past, you probably already know it. Kinetic energy equals 1/2 times m times v squared. This can be put into the triangle. If you don't like the triangle, then ignore it. If you do, then pay attention. Those three values, after you cover up the equal part, you can see that they're all three being multiplied. So I have to manipulate the triangle. So that way there's three places at the bottom, 1/2 mv squared. Now I can go ahead and fill in the last one, which is the equal part, which is KE. That's what it looks like on the triangle. KE stands for kinetic energy. And it's in a joule. M stands for mass, and it must be in kilograms. V stands for velocity, which must be in meters per second. Okay? Now you've got a couple of equations to work on over here. First equation says determine the kinetic energy of, so question mark KE, a roller coaster that has a mass of 625 kilograms, which is a good number, a good unit, and that it's moving at a speed of 18.3 meters per second. So that's a good value too. Let's go ahead and do our math. KE equals 1/2 mv squared, or 0.5 times 625 times 18.3 squared. Go ahead and multiply your numbers together. Don't forget to square that number over there. And then you're going to get an answer in joules. Let's go to the next question. It says here, though, if the roller coaster car in the question above was moving twice the speed, then what would the new kinetic energy be? Okay, so let's go ahead and do that. What is the velocity? The velocity equals 18.3. But they're telling me, though, that it's going to be twice the speed. And so in that case, then, 18.3 times 2, so that way we can double it, is 36.6. So let's go ahead and let's work out the math to see what our answer is. 0.5 times 625 times a new value, which is 36.6 squared. That is a squared value. Okay, go ahead and do your math again, but use this number. Don't forget to square it. Your SI unit is going to be in joules. What happens to my answer? Look at those two numbers and look at them, compare them. Did it double? Did it quadruple? Did it go up by 8 times? Did it decrease? What's going on there? Let's turn the page and let's keep going. We have a couple more questions. Missy, the former platform diver for Ringling's Brothers Circus, has a kinetic energy of, just prior to hitting the bucket of water. If Missy's mass is 40 kilograms, then what is her speed? Question mark velocity. We're talking about KE. The equation for KE equals 1/2 mv squared. My V is what I'm looking for. So let's plug in those values of 12,000 equals, I'm going to change 1/2 to 0.5 times the mass of 40 times V squared. Don't forget that's a squared value. What do you do at the end? You're going to square root it. So let's go ahead and look. 40 times 0.5 equals 20. So divide this side by 20. That cancels out. Divide this side by 20. You're going to get V squared equals blank. Not my answer because that is a squared. Please don't forget to square root it so that way you can find the velocity in meters per second. Please go ahead and finish that up. You're going to write a K or a P depending on what you read over here. So this is going to be expected for you to do. And you definitely need to practice at least one completely on your own. So let's leave that one there for you to work on. The next topic we're going to talk about is what we call the work energy theorem. One more time, the work energy theorem. And there's an equation. Yes, it's on the formula chart. It's called the work energy theorem equation. Okay, so now if work is done upon an object, whether a force acts on it that causes it to be displaced or it moves. Okay, so did the object move if it was displaced? Well, yes, it moved. If the object moved, did it gain or lose kinetic energy? Okay, so what happened? If I've got, let's just draw this out. I've got a person and there's a box and they are going to, with a force, apply it to this box and the box is going to end up moving. The question says, did it move if it was displaced? Yes, it did. If the object moved, which it did it gain or lose kinetic energy? Well, it gained kinetic energy. Then what can we conclude here? That a change in KE of a system is equal or proportional to the work done by the system. So for an example, this person over here is about to apply a force and move the box. Once they applied the force to the box, now the box moved. Did the kinetic energy change? Yes, it did. It actually increased. What can we conclude about that? If you, and that one's you, if you did work to the box and you caused it to move, then that means that you transferred your work that you did, you transferred energy from you to the box. And there was an energy transformation that was occurring. Now, when energy transformation occurs, which it could occur, okay, completely, the only way energy transformation or when energy transformation occurs, that's due to work being done to the system. And if work is done to the system, and I don't care, it's because you push the box or because you push the gas pedal on your car for it to go. There was work done to the system. So if work is done, the object moved and the object gained kinetic energy. That's meaning that, or what they're trying to tell you there, what they're trying to get at, is that work and energy are completely, or kinetic energy, are completely related to each other. I can't do any work unless I have energy, right? If you don't eat, eventually you're not going to be able to get up and go to school and do your job and do homework and think properly because you don't have enough energy. And when you do have proper energy, then you can do work and you can physically do work. And when you do work, then you transfer your energy that you have to another object. And now that other object's doing work and it has energy because of you. So both of those energy and kinetic energy and work are completely related to each other. So let's keep going. If an object that possesses some form of energy supplies the force to do the work. In the process of doing work, the object that is doing the work actually exchanges energy with the object. I don't know why there's this big space. Upon which the work is done. When the work is done upon the object, that object gains energy. And the energy acquired by the object or objects upon which the work is being done is known as mechanical, CAL, energy. Let's turn the page. And because of that, we have an equation. Our equation is work equals kinetic energy. Or we can manipulate the equation to say F times D equals 1/2 mv squared. Now, in this case, if you're given all the other variables except for one, then you can go ahead and solve for one of the unknowns. Let's look at a couple of problems here. Question number 1, how much work, question mark W, will 140 kilogram, which is mass, wrecking ball do to a wall if it's traveling at a velocity of 50 meters per second right before it hits the wall? Okay, well, I know that work equals kinetic energy, and I'm looking for the amount of work. So I also know that work equals force times distance. Do I have distance or force? I don't have that. So in that case, I'm going to have to say work equals 1/2 mv squared. Even though that's the kinetic energy equation, energy and work are completely related with each other. So let's go ahead and fill it in. Work equals, change the 1/2 to a 0.5 times 50. Forgive me. That's 140 for the mass.